Making a radiograph is very similar to projecting shadows with visible light. When making a radiograph, we project a shadow of the calcified structures within the body. In this video, I'll describe the 5 basic principles of projection geometry and how we can use these principles in order to make high-quality radiological images. So let's start by making an image with a point source of radiation. Such a source of radiation produces a shadow with sharply defined edges. The dark part of the shadow is referred to as the umbra. Next, let's make an image with a wide source of radiation. Note that the edge of the shadow is less dark, and this zone of grayness is referred to as the penumbra. The presence of a penumbra decreases the sharpness of our image. By decreasing the source of radiation, we decrease the width of the penumbra and increase the sharpness of our image. And this is the basis for the first principle of projection geometry. The source of radiation should be as small as possible. Practically, X-ray tubes that have a smaller focal spot will yield images that have a higher spatial resolution. Next, let's use this source to make a shadow, and we'll mark out the edges of the shadow. In subsequent slides, we will vary the relationship between the source, the object, and the receptor, and observe the impact on the size of the shadow that is produced. Let's start by moving the source closer to the object. When you decrease the source-object distance, you make the shadow larger and you increase the width of the penumbra. In other words, you cause magnification of the image and decrease the sharpness of the image. And this is the basis of the second principle of projection geometry. The source-to-object distance should be as long as possible. So how do we practically apply this information? Vendors of intraoral radiographic machines will provide collimated extension cones that are 8, 12, or 16 inches in length. The longer the length of the extension cone, the less the magnification and the sharper the image. Another practical application is in cephalometric radiology, where we make images of the skull with minimal magnification so that we can compare changes over time. And we decrease the magnification by using a source-object distance of 5 feet. Next, let's move the object closer to the receptor. By decreasing the distance between the object and the receptor, we increase the sharpness and decrease the magnification of the image. And that is the basis for principle number 3. The object to receptor distance should be as short as possible. When doing intraoral imaging, we try to place the receptor as close to the tooth as possible. However, anatomic contours may limit our ability to do this. And in general, when we make a radiographic image, we always place the anatomy of interest closest to the receptor. Next, let's change the relationship between the object and the receptor so they are not parallel. In this scenario, we have caused foreshortening of the shadow, and here we have caused the shadow to be elongated. So principle number 4, the object should be parallel to the receptor. This parallel relationship is the basis for one of the techniques used for periapical radiography called the paralleling technique. We will discuss the paralleling technique in subsequent lectures. We also use this parallel relationship when we do skull and cephalometric imaging. By orienting specific orthogonal planes, we create posterior-anterior and lateral views of the skull. Next, keeping the object and the receptor parallel, let's change the angle of the beam relative to the object and the receptor. And in this example, we have caused foreshortening of the image. So principle number 5, the beam should be perpendicular to the object and to the receptor. So to summarize the principles again, the source of radiation should be as small as possible, the source to object distance should be as long as possible, the object to receptor distance should be as short as possible, the object should be parallel to the receptor, and the beam should be perpendicular to the object and the receptor. So here's a fun fact about shadow casting. Back in 240 BC, this guy Eratosthenes looks at the angles of shadows cast in 2 different cities. And then he uses that information to go on and measure the Earth's circumference. That's incredible! But we are going to do something that Eratosthenes could never do, and that's look at radiographic unsharpness and radiographic magnification. Of course, that's because X-rays were not discovered that time, but nevertheless. So let's start by looking at image magnification. And in this scenario, we're going to do intraoral imaging with an 8-inch cone. Typically, there's about 2 inches additional from the edge of the cone to the patient. So that's about 10 inches for a source to object distance. The object to receptor distance, the distance between the tooth and the image receptor, is approximately 0.5 to 1 inch. So in this example imaging scenario, we get approximately 5% to 11% magnification. On a practical basis, note that you can decrease the magnification by increasing the source object distance and by decreasing the object receptor distance. Next, let's look at geometric unsharpness. In this example, the unsharpness turns out to be 13 microns. Now this might seem a small number, but remember that the width of the pixel in our XDR sensor is 19 microns. So the width of this penumbra, although small, does have practical implications on the eventual image quality. And note that we minimize the unsharpness using a small focal spot, and we can decrease the unsharpness by using a longer source object distance.